So this is going to be surface area for parametric equations. So you've seen this formula in the previous video. So if you want to write it down again, you can. But basically, just to give a little bit of a recap of surface area, just in case you forgot, we did surface area in Calc 1 just with a regular function. Not that it wasn't defined as a parametric equation, but or expressed as a parametric equation. But you had y equals f of x. And basically the idea was that you have this function, and so let's say you have this function, and what you're doing is that you're rotating it about an axis. So if I rotate it about the x-axis, then basically what you're doing is you're taking this curve, and if you rotate it over and over again, you tend to have like these, I don't know, like these little three-dimensional figure, so that you can so it kind of looks like a funnel, like a cone. And we mainly looked at volumes of revolutions when we were doing Calc 1 stuff. But another thing that we were able to do, not just the thing that was inside of it, but we were also able to figure out the surface area around it. So surface area is basically everything that's on the surface, okay? So we're able to do the same thing. So we're extending the ideas of the surface area formula from this guy to now parametric equations. So now this guy is now x is expressed as a function of t, and so it's y. And now what we're going to do is we're going to find this surface area using these parametric equations, and this is basically what it is. So if I say I am revolving this surface or this graph about the x-axis, this is the formula that we'll use. And if I'm revolving it about the y-axis, then this is the formula that we'll use. This ds will depend on this thing, which is basically the arc length. To derive this formula is really horrific, and we won't do that here. But of course, if you have a question, the book has it, or I'm more than welcome to explain to you what exactly is going on. It's a little sophisticated. So let's go ahead and do a problem. So we'll do one of them, just because these problems can take a very long time if you're not doing them correctly. So here we want to determine the surface area of the object by rotating the parametric curve. X equals 9 plus 2t squared, and y equals 4t, and t is from 0 to 2. So, and we're revolving it around the x-axis, okay? So these problems can get really complicated depending on how horrible the parametric equations are, and it's really easy to just make the integral not solvable afterwards. So all we got to do is just look at our equation. Since we want to do it about the x-axis, we know that we're going to use the integral from 2 pi y ds, and we know that ds is going to be equal to the square root of dx over dt squared plus dy over dt squared dt. So that's what we know. Okay, so so this is going to be our surface area formula, but before we get to this, we need to figure out what ds is. So let's first start off with ds. Let's start off with the derivative and then plug it into ds. So dx over dt, that's just going to be this 4t, and then you take dy over dt, and that's just going to be this 4. So now when you plug it into ds, you're just going to get the square root of 4t squared plus 4 squared, which is going to give me the square root of 16t squared plus 16. Okay. I can maybe try to make that a little better. Oh, I forgot my dt's. I can take out a 16, get 16t squared plus 1 dt, and you're just left with 4 square root of t squared plus 1 dt. So already, because we have a square root of something squared, typically there's going to be times where you might have to use trig sub. Let's hope that that doesn't happen, but don't be surprised if it does. Okay, so surface area S is equal to the integral from 2 pi y ds. So now remember, my integral is going to be from, we'll just figure out about the limits of integration in a little bit. We have 2 pi. And then we need to figure out what y is. Where y in this case as a parametric equation is 4t. So that's just 4t. And then you have the ds. The ds is going to be this thing that we just calculated. This guy. So it's going to be times 4 square root of t squared plus 1 dt. Now t in this case, we're doing it from 0 to 2. So it's going to be from 0 to 2. So you're going to have the integral from 0 to 2 of what is this going to give me? So this is going to be a times 2. This gives me 32 pi t square root of t squared plus 1 dt. So I'm going to take out the 32 pi. I'm going to have the integral from 0 to 2 t square root of t squared plus 1 dt. Okay. Here we're going to do another u sub. Okay, so of course you could use trig sub if you want, but u sub I think it's a little easier. So let t squared plus 1 be u, and then du is going to be 2t dt. So 1/2 du is equal to t dt. So you're left with 32. Whoops. Pi. And then you just have a 1 integral from 0 to 2. These are for values of t's. Then you're just going to have a 1/2. And then you're going to have a u to the 1/2 du. Okay. And then you're just going to have this 32 pi times 1/2. Take the integral of this. You're going to have u to the 3/2 times 2/3. Okay, and then from 0 to 2, these are for t. You can see that the 2's cancel out, so I'm left with the 32 pi over 3. And then u in this case was t squared plus 1 to the 3/2. Plug in from 0 to 2 now. And then what you're going to get approximately when you plug this is around 341.15. Okay. So these problems can get really complicated if you have a trig sub, but you want to be able to use whatever toolbox you have. You won't really know until you start plugging in these values. So if you take the derivatives and you plug them into the formula, plugging it into the formula is super easy. What's going to be difficult is these integrals, but you should feel really comfortable with the techniques that we've learned and be able to do trig sub or integration by parts or whatever.